I haven't really covered central ray tracing as a separate topic. In lecture 6 we covered vergence. In lecture 14 we covered transverse and axial mag, but we haven't covered central ray tracing as a separate topic. So let's kind of do that now. Let's say that we have a lens here, and let's make it a plus lens of indeterminate power. And the idea is that if we were to draw vergence lines with this lens, vergence lines, let's have our object here, which of course is a candle. Vergence lines always start out at a point and always end in a point. Like this. There are 4 questions that we can be asked in ray tracing problems, in vergence problems like this. The first one is, where are the objects, what are the powers of the lenses, all of that sort of stuff, which is really kind of one question. The second thing that we can be asked is, what is real and what is virtual? The next thing that we can be asked is, what is upright and what is inverted? And the last question that we can be asked is, what are the relative sizes, which is the mag question. The first 2 of these questions are answered using vergence. The second 2 questions are answered using central ray tracing. We'll call it RT for ray tracing. So it's ray tracing that we're going to be dealing with now. Anyway, let's go back to our drawing here. And we have our object here. We're going to label this O. And we have the image, which is going to be formed over here. I'm not telling you whether it's upright or inverted yet, but we're going to call that I. And the first 2 questions, where and what are the powers, we're not going to worry about that now. Although, you know what? Let's worry about it anyway. Let's say that this distance here is equal to 1/2 meter. And let's say that this distance here is equal to 1/4 meter. And we're going to ask, well, what is the power then of the lens? And of course, as the rays of light emerge from the lens, they strike, when the rays of light emerge from, in this case, the base of the candle, they strike the lens with a vergence, well, 1/2 meter to the left. To the left means minus, and 1/2 meter means 2. So they strike the lens with a vergence of -2. What is the vergence of the rays of light coming out of the lens? Well, anytime that we ask what the vergence is, we answer with a question. And the question is, where do the rays of light converge? And in this case, they converge 1/4 meter to the right. To the right means plus, 1/4 meter means 4. So the rays of light coming into the lens at a vergence of -2 exited with a vergence of +4. What must the power of the lens be? It must be +6. Okay. So that was question number 1 here. Question number 2, real and virtual. The order should be object, lens, image. As long as nothing's offside, they are all real. So if an object is to the left of the lens, as long as we obey the convention that the rays of light are moving from the left side of the diagram to the right side of the diagram, as long as the object is to the left of the lens, it's real. If the image is to the right of the lens, it's real. So we've solved real and virtual. But we haven't covered central ray tracing as a topic, so let's cover that now. First of all, since we drew this as a vergence problem, with vergence, rays of light start at a point and they end at a point. But central ray tracing is not like that. I'm going to erase this, and I'm going to redraw the same diagram, which looks something like this. And we have that there, and we have our candle, naturally. And we have the power of this lens. We don't really care what it is, although we actually do care what the distances are here. And this distance, we said, is 1/4 of a meter. And we always try to use meters because in physics it's a great help to keep, oh, see, I made a mistake and you didn't even catch me. This is 1/2 of a meter. In physics we always try to keep our units consistent, and then this was 1/4 of a meter. And this is where the image is. So, what is special about the ray of light that we've drawn here? Well, this would have shown up in the divergence diagram too. Would have started out at the base of the candle and diverged and then converged over here. Well, what's special is that this ray of light passes through the center of the lens, the optical center of the lens, the nodal point of this lens. And in doing so, it emerges from the lens undeviated. And in fact, any ray of light that would have passed through this lens through the optical center would emerge from the lens undeviated, unbent. Well, we have one special ray here, and that is the ray that has started out at the base of this candle. And what we're going to do is we're going to draw one more central ray, which is a ray that's going to start out at the top of the candle and is also going to pass through the optical center of this lens. And let's see what it does. It hits the optical center of the lens, and nearly hits it, and emerges from the lens undeviated. The ray of light carrying the information, a ray of light carrying the information of the bottom of the candle is this ray of light here. This ray of light carries data about the top of the candle, so that where the image is formed, and again, using central ray tracing, we don't know where the image is formed. That's something that we figured out initially using divergence. Where the image is formed, the data about the bottom of the candle is going to be along this line, and the top of the candle is going to be along this line. So our candle is going to look like this. Okay? We have one central ray here, which was in common with the divergence problem, and one central ray here, which represents data for the top of the flame. Using that, we can see that the image is inverted, not upright. And we can also calculate the relative size, and you'll remember this from the transverse magnification lecture, that all that we're going to do is we're going to take the ratio of the bases, and that's going to be the ratio of the heights. This base is 1/2 meter, this base is 1/4 meter, or half that base's length. Therefore, this guy here, if this is x high, this is going to be 1/2 of x high. The ratio of the heights is equal to the ratio of the bases. Anyway, if that's not clear, you can review the transverse mag problem. But I promised you more than this today. I promised you that we would be solving a multiple lens problem. And I kind of told the truth and I kind of lied. First of all, let's map out our multiple lens problem. We'll start out with our object, which is a candle. None of these problems work if the object is anything other than a candle. And we have one lens here, and this lens is going to be +6. And I'm going to give you quite a bit of data here. I'm going to say that this distance here is 1/4 of a meter. And I'm going to have another 1/4 of a meter here to get us to an unknown lens. And as an unknown, I'm not going to specify whether it is convex or concave. I don't want to give it away. And it is of some power. We don't know what the power is. And then I'm going to tell you that the image is formed 1/2 of a meter to the right. And I want to know a whole bunch of things. I want to know the 4 questions, which is where and what powers, what's real and what's virtual. I want to know what is inverted and what is upright, and I want to know what the relative sizes are. And I want to know it not only for the final image, but for the intermediate image as well. So this looks relatively complicated. The thing to keep in mind, and the reason that I said that I lied, is that as ophthalmologists, we're very simple-minded, and we can't handle multiple lens problems. So we're not going to treat this as a multiple lens problem. We're going to treat this as a multiple single lens problems. And what I mean is this. We're going to label this guy here object number 1. We know somewhere in here is going to be image number 1. We're going to call this thing lens number 1. Almost out of your field of view there. You should still be able to see that. And somewhere is image number 1. This guy here is lens number 2. Now, as ophthalmologists, as problem solvers here, we are only able to keep in our mind one object, one lens, and one image. And we cannot imagine anything else. So all that we're going to do is we're going to view everything with a subscript 1, and we're not even going to see anything with a subscript 2. To us, this lens is invisible. I'm going to ignore it. And we're going to solve this initially as a Virgins problem because, you know, before we can solve anything using central ray tracing, we have to know where things are. So let's go ahead and solve this then. With Virgins, things start out at a point and up at a point. So we're going to do the Virgins for the base of the candle. And the first question is, what is the Virgins of the rays of light? What's the Virgins of the rays of light here? You remember? It's infinite. Because Virgins, when I ask you what the Virgins is, you say, where do the rays of light converge? And then the Virgins is 1 over that distance. If they converge to the left, it's minus. If they converge to the right, it's plus. And, of course, here, the distance to where the rays of light converge is 0. So 1 over 0 is infinity. Anyway, trivia. We want to know what the rays of light are, what the Virgins is of the rays of light just as they're hitting this lens here. And when I ask you what is the Virgins at this point, you answer in Talmudic fashion with a question, which is, where do the rays of light converge? And from this vantage point, they converge 1/4 meter to the left. 1/4 meter means it's a Virgins of 4. To the left means that the sign is minus, so it's -4. And what is the Virgins of the rays of light as they emerge from this lens? Well, it's simple math for us. -4 plus 6 is equal to +2. So +2 means that the rays of light converge where? Always and forever, +2 means 1/2 meter, and plus means to the right. So 1/2 meter to the right, let's see, this is 1/4 meter. Another 1/4 meter would be about here, right? We'll say this distance here is 1/4 meter from here to here. And we know that the rays of light converge here. So I'm just going to draw the rays of light converging to that point over there. This is going to be image number 1. Okay, so first of all, in concession to the fact that I recognize that there really is a lens here and that I recognize the lens is going to do something, I'm going to acknowledge that the rays of light as they pass through here are not going to be exactly straight lines, but are going to deviate somehow. We don't know how yet. And I'm going to do that just by making this line broken and say, okay, whatever. There's a lens there. I'm not worried about it. But I'm going to acknowledge that it does something. So all that I can see here is object 1, lens 1, and image 1. First question. Well, actually, first question's answered. That's all of these sorts of things here. Second question, real and virtual. Okay? Is object 1 real? Well, it's to the left of lens 1. So it's real. Is image 1 real or virtual? Well, it's to the right of the lens, and we said that if the image is to the right of the lens, it's real. So image number 1 is also real. Now we're going to work with subscript 2. Image number 1 is equal to object number 2. Right? You knew that. That image number n is identical to object number n plus 1, right? In a multiple lens problem, or a multiple single lens problem. Anyway, now we're dealing with object number 2 and lens number 2, and we completely ignore anything that has subscript 1. I can't see this, I can't see this. I can only see this to the extent that I recognize it as object number 2. Now, object number 2, lens number 2. The question is, what is the divergence of the rays of light as they enter the lens? Now, in which direction do the rays of light move? Are they moving from the object back to this lens? No. In these problems, the rays of light always move from the left to the right, as long as we're not dealing with a mirror problem, which thank goodness we are not doing right now. All right, so the rays of light entering the lens are entering from this side, according to our arrow here. And what is the divergence of the rays of light here? Well, again, anytime that I ask you the divergence of the rays of light, you answer with where do the rays of light converge relative to object number 2. They converge 1/4 meter to the right. 1/4 meter means that the absolute value of the divergence is 4, and to the right means plus. Now, we know that the rays of light, I've already given you at the start of the problem, that image number 2 was over here. That was a given. That means that the rays of light emerge. I'm going to draw solid lines now because we know that the rays of light really are moving this way. The rays of light converge there. Where is that? That is 1/2 meter to the right. 1/2 meter to the right. What does that mean? Well, 1/2 meter means that the divergence at this point, and again, it's 1/2 meter to the right from this point here. 1/2 meter means that the absolute value of the divergence is 2. To the right means plus. Whatever this lens did, it took +4 and it made it into +2. So what must the power of lens 2 be? What can make +4 into +2? Oh, you know the answer. Don't hold back. It is -2. So lens number 2 has a power of -2. Lovely. And we know where image number 2 is. Now we can ask about real and virtual. First of all, is object number 2 real or virtual? Well, it's to the right of lens number 2, so it's virtual. Now, a lot of people get hung up on the idea of a virtual object. How can an object be virtual? It can be virtual. It's just object number 1 can't be virtual. For an object to be virtual, it really has to be an intermediate object, as this one is here. Does it bother you that this intermediate thing here is a real image and a virtual object? No, it doesn't bother you. It's just words. Anyway, object number 2 is virtual. Image number 2 to the right of the lens is real. Okay, so we've answered the first 2 of our questions. And again, we have not done any multiple lens problems. Here we just did 2 single lens problems in sequence. Okay, so let's move on now and answer the second 2 questions, which is what's upright, what's inverted, and what are their relative sizes, or what is their transverse mag. And for this, we want to get rid of the divergence lines. Let's see if I can excise them without causing too much collateral damage. Because all that we're interested in now is the locations. And we don't actually need the lens powers either. Let's get rid of them. We already have our answers. Lovely. Okay, so to reiterate here, we have object 1, lens 1, image 1, and we have object 2, lens 2, image 2. And we're going to maintain the idea that we're simple-minded and that we cannot hold in our little monkey brains more than one object, lens, and image at a time. So we're only going to deal with the subscript 1s first, and we're going to ignore all subscript 2s. For central ray tracing, we need 2 central rays. We already have one of them here, right? This is the central ray that represents the data about the base of the candle. The other central ray that we want is the central ray that represents the data from the tip of the flame. So lens number 1, the optical center is here, and we're going to draw a line going to image number 1 through the optical center of lens number 1. And, almost right off the side of the diagram here. Now, what does this mean? It means that the data in the image for the base of the candle is along this central ray, and the data representing the flame of the candle is along this central ray. So we draw the base here and the tip of the flame here, and I see I as always have made this diagram overly crowded. Right, this distance here was 0.5 meters. We remember that, given to us at the start of the problem. And so we'll draw our candle, as I said, and we'll draw it like so. Okay. And you say, but wait a minute, we didn't take into account what's going with this lens. It's because I didn't see it. Because it is subscript 2, I ignore it completely. Okay, image 1, inverted or upright? Well, I think it's pretty clear that it's inverted. Object 1 being upright here. Number 2, the relative size. If this is height x, then what is image number 1? Well, the base of this triangle is equal to 1/4 meter, and the base of this triangle here is equal to 1/4 meter plus another 1/4 meter, so it's 1/2 meter. Therefore, this thing must be a height of 2x. I'm going to come back to the mag question with this later. But anyway, we have that now. Let's choose a different of our colors for subscript 2. Let's make subscript 2 green. Subscript 2, it's the same process. We start with one central ray, which again represents the base of the candle, travels along our whole diagram here. We need a second central ray that represents the data from the top of the flame here and passes through the center of the lens. Which lens, you ask? I only see one lens. I only see things with subscript 2. In this case, it's lens sub 2, and I draw a line from the tip of the candle to attempting to hit the center of lens 2, and it continues going on that way. Unfortunately, there's nothing over here that I care about right now. I have to get to image number 2, and I'm going to get to there by extrapolating backwards. Over here, careful not to get outside of the bounds of my diagram. Okay? This is the data that represents the base of the candle. This is the data that represents the tip of the candle. So I draw my candle thusly, with the flame like this. Image 2, inverted or upright? Well, it's inverted. You can see that, it's upside down. And what about its relative size? Well, we have the base of this triangle here as 1/4, right? This is one triangle here. Remember this is from the transverse mag lecture? And this is the second triangle here. The base of this triangle is 0.5 meter. So if this is 2x high, then this must be 4x high. Easy peasy. You know, there's one more question that we could ask, which is this. Let's get rid of all of this stuff. And I'm going to make a kind of a bare bones version of the diagram that we just saw, which is this. We had our first image here, and we had one lens, and we had another lens. Now I can draw it as concave-ish. And we had one image here, and we had another even larger one here. Now I don't care about the distances, I don't care about anything. But here's a question. Let me get rid of the lenses. Well, I'll leave the lenses. This was x high. and this was 2x high, and this was 4x high. The question's this: what if this thing was a units wide? How wide is this one? Is it 2a? No, I hear you shout. Of course not. It's 4a. Because axial mag sub axial, is equal to transverse mag squared. This is 4a, which would make this, everyone shout it at once, 16a, or 4 squared. Anyway, that is how we solve multiple ends problems. And the trick to solving multiple ends problems is to be simple-minded, and that will always get you through. Thanks. And as usual, any questions, you can write to me at jyoungmd@gmail.com. And you can find the optics lectures, although I suppose that you've seen them already, on the website. Open ophthalmology.com. Bye-bye.